Good morning, everyone. My name is Dr. Grant Hall. I'm from the University of Pretoria, where I run the stable isotope facility there. And I'm going to talk to you today about a bit of work we're doing helping to detect honey adulteration in South Africa using stable isotopes. So it's a worldwide problem that products of high commercial value, such as wine, cheese, olive oil, vanilla, and including honey, are often adulterated, and this happens in increasingly cunning ways. It's a bit of an arms race between those of us trying to detect adulteration and those trying to adulterate. And this is done primarily to increase profits. Honey is one of these food substances that gets adulterated quite regularly. And this can be done in a number of different ways, including using items such as low-cost fructose or corn syrup, which is a C4-derived product. And I'm going to go into a little bit more detail about what a C4 product is. Other plant-derived syrups such as rice syrup or banana syrup. There may be misinformation on labels, and there's often also mixing of poor quality honey with high quality honey to try and increase yields, and this mixed product is then sold as the higher quality honey at a higher price, obviously. Considerable research has been done using stable isotopes in the Northern Hemisphere, dealing with authentication, as well as the geographic location or origin of products. And this includes honey, some of the products that I mentioned earlier, as well as alcohol. And the European Union has a substantial database on these products, as well as strict laws regarding the production and sale of alcoholic beverages and honey and other important food items. South Africa too has considerable regulations and quality controls pertaining to the honey and associated products. We also do, although it's not often well known, that we do have the knowledge and the technology to determine and maintain the quality of such high-end products such as honey. The downside is that this knowledge is not always adequately communicated to relevant stakeholders. So the scientists that have the technology and the know-how don't always speak to the stakeholders and the producers of the honey. We're going to be I'm going to be talking about stable isotope ratio mass spectrometry, or IRMS, as a forensic tool. The application of IRMS as a forensic tool is relatively recent, but has become an integral part of forensic investigations. And this includes food fraud, but has wider applications as well, including the location and tracing of explosives, various types of drugs, and also the identification and repatriation of unknown human remains. This was first recognized in the 1970s, but it's only since the 1990s that stable isotope analysis has been increasingly used in this field. This is largely due to the improvement in equipment, a better understanding of how isotopes work in nature and how they are affected both in organic and inorganic materials. And the success of this method, and it is a successful method, relies on the ability of the mass spectrometer, which is the instrument used to measure stable isotopes. It allows us to measure incredibly small, naturally occurring differences in the amount of isotopes in material, which can be used as evidence to determine adulteration and even geographic location. So what are stable isotopes? Stable isotopes are atoms of the same element that have the same number of protons and electrons, but they differ in the number of neutrons. And this tiny, significant difference allows us to do a lot of really, really cool stuff. They are referred to as stable isotopes because they're not radioactive. They do not undergo radioactive decay. And there are several stable isotopes that we use regularly in a wide range of research. And these are carbon, nitrogen, oxygen, hydrogen, and sulfur. Basically the building blocks of pretty much everything around us. Isotope specialists have been working on understanding all the processes and how isotopic composition changes of various materials, products, and tissues, and how these are affected by the local environment, processes such as fractionation and metabolic processes. And this has been going on for decades, and can now be applied in practical terms, in terms of like working in a forensic field. Due to tiny mass differences, the isotopes of a chemical, such as carbon or nitrogen, they behave slightly differently during biological, chemical, and physical reactions. These natural variations are incredibly small, and we measure them in parts per thousand, and, as I say, are measured with a very sophisticated piece of equipment called isotope ratio mass spectrometer. These variations can be used to explain and understand a range of processes, such as plant and animal responses to climatic change or environmental shifts. Movement patterns can be detected, and we can also get to understand dietary behavior. And very importantly, which relates to the work we're doing with the honey, we can also start determining geographic origin. So to give you an idea, this is what the mass spectrometers in my lab look like. We have two of them. One of them we will be specifically geared up for analyzing samples such as honey. A little bit of background information. So some of the earlier work that I mentioned discovered that substances such as limestone, the carbon dioxide in the atmosphere, and different types of plants, whether they're growing in a marine environment or a terrestrial environment, have characteristic carbon isotope ratios. This is very important, that we can measure these very clear differences, particularly because we are focusing on honey, which is derived from plants. Terrestrial plants can be divided into three groups, and this is based on the way they photosynthesize. So the way they use sunlight and carbon dioxide from the atmosphere to grow, make tissues, produce flowers, leaves, nectar, and so on. And they can be divided, these three groups are C3 plants, this is including all your trees and shrubs, and cold environment grasses. In South Africa, we have very few C3 grasses, and they are very limited in their distribution. C3 plants obviously include the majority of your flowering plants as well. Then we have C4 plants, which are your grasses, and obviously Southern Africa has a lot of grasses, and these are all C4. Then, to complicate matters, because things can't be too simple, we have CAM plants, and these are your succulent plants, and they include species such as aloes. And in the South African context, when it comes to honey, this will be of relevance, and I'll show you why shortly. Right, so C3 plants have a carbon isotope range of between -20 to -35 per mole, and this is based on years and years of analysis of hundreds and hundreds of different plant species across the globe. Based on the definition of honey, honey is supposed to be predominantly derived from C3 plants, and therefore should have similar values. Then we have our C4 plants, and you can see here their carbon isotope values are markedly different, ranging between -9 to -14 per mole. Honeys that come up with values in this range may be considered to be adulterated with something like sugarcane syrup. Then we have CAM plants, your aloes, and they have a very wide range. You can see they're -11 to -33 per mole. They utilize both C3 and C4 style photosynthetic pathways, depending on the time of day. And in South Africa, we have quite a bit of aloe honey produced. And if we purely used stable carbon isotope ratios to determine whether an aloe honey is adulterated or not, if it comes out in the C4 range, the chances are it will fail that test. So this is something that needs to be worked on. Stable Isotope Lab has worked with the Department of Agriculture and a number of other external clients doing isotopic authentication of alcohols. And we've worked for the last 15 odd years with these clients using carbon isotope analysis to determine whether products are adulterated or not, or comply with certain regulations. So we use the undistilled products, and we measure their carbon isotope composition using the mass spectrometer, and we can determine whether the product is pure or a mix of C3 and C4 derived ingredients. So for an example, brandies and wines are made from grapes, which is a C3 plant. So you should be getting values of around about -26 to -28 per mole in their carbon isotope ratios. Ciders and perries, which are made from apples and pears, also C3. They should also come out with values of around about -26 to -27. We can also use the carbon isotope ratios to work out the percentage C3 component, and we do that often with the ciders because the minimum standard is 80% apple product in that cider. Just to give you an idea, here's a few examples or samples that we've run over the years. The blue dots at the top there represent stable isotope values for products that were adulterated, so they're all in the C4 range. These were supposedly predominantly wines, and as you can see, their values are in the C4 range, which is an indication that they are fake, basically. Then we have several samples that are in yellow in the middle. These are samples that are a mixture of C3 and C4 products and also may be considered partly adulterated. And then right down at the bottom, the pale yellowy white dots there are products that comply and are made from what they're supposed to be made from. All right. So in general, as I've mentioned earlier, most honey should be derived from purely C3 plants, and this is based on the Codex Alimentarius definition. But as I've mentioned earlier as well, there may be some exceptions, and this is including South African aloe honey. These exceptional types of honey are not always accounted for, and therefore will fail certain tests, particularly if they are sent overseas for analysis, which has been the case. Most of the isotope analysis that's been taking place over the last few years since the issue of honey adulteration appeared on the horizon have been done at European laboratories. All right. We at the Stable Isotope Lab have been working quite closely with the Social Research Group, SURGE, and the Department of Agriculture, and we are trying to establish the appropriate methods that are internationally accepted to carry out isotopic authentication of both local and imported honeys, based currently on the ratios of bulk honey, but we're also moving to where we will be extracting protein from the honey and using the equation that you can see there on the right of my screen, where we use the carbon isotope ratio of the bulk honey or whole honey and the extracted protein. We get the stable isotope ratio of the protein. And we use this formula to determine the percentage adulteration. If the value that's calculated is higher than 7%, then that product may be considered to be adulterated. There has been a little bit of work done in 2014 at a lab in South Africa, but unfortunately that isotope facility is no longer operational. Here on the screen we have some real-time data based on the analysis of a number of samples that we've done at the University of Pretoria lab. And the values right down at the bottom, between the -25 and -28 range, those are all honey products that comply and satisfy the internationally accepted range of values for stable isotopes of honey. The ones a little bit further up, between -20.5 and around about -23.5, those products are just on the edge and fall into what I would call a grey area and may be considered as suspicious, and further analyses of these products would have been necessary. And then further up we have a product Surge number 1, that's its laboratory number. This product came out at around about -14.4 with its carbon isotope ratio, and this product is a clearly adulterated honey product. The three values up at the top, the ANU sucrose, glucose, and brown sugar, are all derived from sugarcane, which is also a type of grass and is a C4 plant. And you can see that honey number 1 there has values very close to that of these sugarcane derived products. So clearly an adulterated product. Right, just to summarize there. So I just want to reiterate that we measured bulk or whole honey, and the majority of the samples that we looked at showed that they are accepted and can be considered as pure honeys. The one that stood out clearly was surge number 1 with a value of minus 14.4, and this particular honey was very, very definitely an adulterated one. It was basically a sugar syrup flavour to taste like honey, but not really. And a number of the local samples that we also analysed fell in the questionable area of carbon isotope values. And so there's a bit of uncertainty about the purity of these products. But the question is, does this indicate that these samples were indeed adulterated, or are the isotope ratios reflecting something else that we need to account for? Okay, so there's a number of goals and requirements that I'd like to present to everybody here. We still need to do a lot of background research and capacity building so that we can ensure that honey products are accurately analysed, as there are a number of factors to account for. I'm going to specifically focus on those that affect the isotopic analyses. We have an incredibly diverse flora. We're looking at around about 30,000 species of plant which bees can utilize. We also have an incredibly variable climate across South Africa. If you compare, we've got winter rainfall areas, we've got intermediate rainfall areas, we've got summer rainfall areas, we've got very dry areas, very hot areas, and so on. And all these factors will also influence the carbon isotope ratios of plants, and thereby any products derived from these plants, such as honey. So what we need to do is look at the variation in the carbon isotope values and other chemometric values over a long period of time. So we need to do seasonal data, and we need to collect that over several years and include isotope analysis, pollen analysis, and a variety of other analyses, all working on the same samples. In addition, we also need to do some experimental work to determine the effects of anthropogenic manipulation, such as artificial feeding or the inclusion of additives. Right. To generate this aforementioned data will require a lot of collaborative work and information transfer. And this is very important, and this is, I think, one of the key goals of this workshop, is to allow the transfer of knowledge and information between scientists who have the specialized knowledge and the technology, and the honey industry, both the producers and those that are responsible for quality control and basically policing the industry. We need to do interlab comparisons and a lot of cross-disciplinary research to ensure we comply with the currently internationally recognized and accepted methods and techniques. And it is possible. We do have it. We just don't have enough people trained at the moment. All right. So the ideal goal will be the formation and maintenance of a database of long-term analyses of South African as well as imported honeys over seasons, geographic regions, such as you can base this maybe on provincial differences, and honey varieties as well, so such as your monospecific types of honey, such as aloe honey, fynbos honey, eucalyptus honey, and then your mixed floral origin honeys. And this data should be accessible to everybody. Currently, there are 3 stable isotope labs in South Africa, and we are all oversubscribed in terms of requests for isotope analysis. The labs are my lab at the University of Pretoria, Itemba Labs, and the University of Cape Town. The demand for stable isotope analysis, or acronym is SIA, is extremely high. I currently am involved in projects for a number of students at the University of Pretoria from various different departments, and I also provide services, analytical services, for between 7 and 12 other universities and technical research facilities around the country, over and above doing work for the Department of Agriculture and other clients such as Distel. Unfortunately, all the equipment at the labs is aging and is expensive to replace. We're looking at millions of rands per machine. And the problem as well is there's a limited number of people that actually operate these mass spectrometers and maintain them. Not simple machines, and it takes quite a lot of experience to work with them. Right, so we need to build up capacity. We need technical professionals to provide the necessary understanding and experience of these scarce skills, and we need to build and expand the current equipment that we have available. The other problem is, and this was something that was raised at a meeting that I attended a couple of weeks ago, is it was a matter of accreditation. The 3 labs that I've mentioned here are all predominantly teaching and research facilities. We're not accredited. We also don't have the person power to ensure compliance with all the necessary requirements, particularly if we're going to try and use the results as a form of evidence if things should ever go to court. The science is sound, it's just that we don't have the ability to comply with all the requirements, such as chain of evidence and so on. That's a problem that should be addressed, and it's a national issue. But the key take-home points are we have made a start. In fact, one of the earliest analysis was done in 1987 at the University of Cape Town, and colleagues of mine that actually taught me, I was originally at the University of Cape Town, did a short paper with a couple of samples where they were trying to use bulk carbon isotope analysis and try and develop this as a forensic tool. Nothing came out of that. And then, as I say, there have been a number of more recent pieces of work done to try and use various analytical techniques to pick up and determine degrees of adulteration. We're now at the isotope lab at the University of Pretoria are now trying to focus on making this more readily accessible to the industry. But as I say, at the moment there's only a few people doing it. In fact, there's only one person doing it at the moment, that's me. And we need to train up and get more people involved. Great, thank you very much. If there are any questions.